And thank you for joining us today for our webinar. As always, let's give it a couple of more moments until everyone joins and settles in, and then we can start. Good, I think the numbers have slowed down. So for those of you who joined just now, welcome again. Thank you for joining us. So let's take a look at the agenda. Okay, sorry. Sorry, I have some noise issues. So let's take a look at the agenda as promised. So for the beginning, we have a brief introduction to Solargis for those of you who don't know us yet. And since today's topic is uncertainty, we'll talk about why it matters to project stakeholders, and then we'll dive into what goes into building a probability distribution. We'll also talk about how we calculate the uncertainty and the three main factors that influence the calculation. We'll finish it off with a sample project on which we will demonstrate the importance of reducing PV yield uncertainty. You can submit your questions through the Q&A panel on your right. We'll be monitoring them throughout the webinar, and at the end, we'll have some time to answer them. A recording will be shared with you by email and posted on our website shortly after. Before we start, let me introduce you to your host today. My name is Dorota. I'm the product marketing manager. And today I'm joined by Pablo, who is our technical writer.
Hi, everyone.
And Pablo specializes in technical writing and content marketing. He's an industrial engineer with experience in the renewable energy and software development sectors. And together with us, you'll be spending the next 40 minutes. So let's dive in. For those of you who aren't familiar with our company, let me briefly introduce you to Solargis. We're best known for our high-quality solar and meteorological data. For a long time, Solargis has been recognized primarily as a data provider, and in recent years, we've grown from being just a data provider to also offering software solutions. And with these combined services, we cover the full PV power plant lifecycle, from pre-feasibility and planning to operation and management. We've been on the market since 2010, and over the years, we've developed our own technology as a result of long-term R&D initiatives that are at the core of our products. The Solargis team has more than 130 employees. We are headquartered in Bratislava, Slovakia, with branches in Canada and Singapore to be able to support our customers from all around the world. Today, we work with more than 1,200 customers in over 100 countries, and each year, our data, software, and services support more than 9,000 utility-scale solar projects. So today, we're talking about PV yield uncertainty. And here's something interesting. Whether you're an engineer, an investor, or a lender, you might have very different priorities for your solar projects, and you might be asking fundamentally different questions. If you're an engineer, you look at the design and you wonder if this physical PV power plant will actually generate what you designed it for. If you're an investor, you want to know if this asset is going to bring you the promised financial returns. And if you're in the shoes of the lender and you're providing the debt for the project, you ask the most conservative question of all. Can this project safely repay the loan even if the weather underperforms? So everyone has a different goal, but they're all looking for a single source of truth. And that's where uncertainty plays a really important role. Now, let's move ahead because Pablo will talk about how to estimate the uncertainty of your simulated PV yield. And at the end, we'll show you how this affects the expectations of these three stakeholders. Over to you, Pablo.
Thanks, Dorota. Yes, the stakeholders' concerns you just presented, and we are analyzing today, point to a simple fundamental truth, which is simulation is not reality, right? And whenever we model an asset, we need to account for several layers of differences with the real world. We have deviations in our models. We have unrealistic user inputs too. And on top of that, we have, of course, the natural cycles of weather, together with the shifts we expect from climate change as well. So because of these real world variations, we can't give the stakeholders a single absolute number or a simple yes or no response to those questions. The answers to these three stakeholders are a little bit more complex, I would say. And to be able to give a reply, we need to include what we call probability scenarios. So when the engineer wants validation of the power plant design against reality, our answer becomes with a XX% of probability, a specific yield of PXX kilowatt hours per kilowatt peak per year will be reached. And on the other hand, when the investor asks about how sure we can be about the financial returns, we may answer, okay, with such XX% probability, the expected annual return on equity will reach a certain value. And finally, when the lender asks about repayment safety margins, we can answer with a XX% probability, the project will generate an annual revenue that will exceed the requested debt service payments. And here the bank can set the requested revenue to be at least 1.5 times higher or 1.30 times higher, or whatever ratio that makes them feel comfortable. For us now, the next question would be, how do we actually build the probability scenarios for our expected PV yield? So although it is a simplification of reality to keep things clean and functional, the industry assumes that deviations will follow a standard normal distribution. This assumption works well in most cases, okay? But it is possible that in future research will identify another probability distribution that better reflects real world behavior. For now, however, the normal distribution remains a good balance between theoretical accuracy and practical applications. So having a normal distribution means that if we draw a curve of the expected value versus its probability, the center of the curve represents the average and most expected value. We call it P50. And there's a 50% chance the project will generate more than this number, and a 50% chance it will generate less. But banks don't really fund projects based on the same probability as a coin flip, right? So lenders want to know what happens in a conservative scenario. They know that things in the real world, as we do, don't follow the average trend. So they look at other figures, like for instance, P90, which represents the value that has a 90%, in this case, probability to be exceeded. Or P99, which is the same concept, but for a 99% probability, which is even more conservative. To calculate any PXX scenarios, we make use of the normal probability properties. We take the P50 and apply a multiplier of the standard deviation, which is directly related to the uncertainty value. Following this, P90 is calculated by taking the P50 average and subtracting 1.30 to 82 times the standard deviation. Okay, and just a small clarification here. In practice, we could, but we don't see just one time standard deviation when we are reporting our PV uncertainty scenario. And this is because that would make a strange P84, which does not sound like a number we would work with in our daily lives, right? So to make these scenarios easier to use as a reference, we work with this I have just mentioned, P90, P75, P99, or any other PXS that may be practical to us. And to obtain those, we just apply a different multiplying factor. Now, let's look at these two curves we are showing here on the screen. We clearly see that if you push your uncertainty down, the P50 is associated with a higher probability when looking at the vertical axis. So now it's like you have a steeper curve, right? On the other hand, when looking at the horizontal axis, while the total area under each curve remains the same, you instantly have the P90 scenario much closer to the P50 scenario. You can see? So, and this had great benefits for your project that we will see later. Okay, so in project development, let's say uncertainty doesn't just come from one place. It rather accumulates across a long calculation chain. So to calculate the final project uncertainty for the annual expected yield, we have to sum several factors. We can group them into this, we are going to call these pillars, which we will see later in more detail, okay? So the three pillars are irradiance model uncertainty, PV simulation uncertainty, and the third one is interannual variability. And to combine all these three uncertainties, we are going to assume that the individual variables are independent and normally distributed as well, okay? This is going to allow us to use the root sum square aggregation method, following the formula that you can see on the screen.
Thank you, Pablo. So now is the time to do a poll, and we'd like to invite every one of you to engage in the poll. So give me 1 second to just launch the poll. Good. So now you should see on your GoToWebinar screens the question which we'd like to know your opinion on, and that is that which factor is the biggest source of uncertainty in your current project assessments? So the options are solar irradiance model, PV simulation, or interannual weather variability. So you can choose just one answer. Good. Let's give it a couple of more moments until the votes start rolling in. Good. Let's give it 10 more seconds. Thank you very much. Thank you for voting. But before we reveal the actual results, Pablo will walk you through the three pillars of uncertainty in more detail.
Thanks, Dorota, again. So now let's take a look first at the first uncertainty pillar, the solar irradiance model. To estimate uncertainty here, what do we actually need is the question. Well, and before we start, we need a highly consistent model that performs reliably under diverse climatic conditions. Otherwise, estimating uncertainty becomes an impossible task, okay? So first we have this consistent model to analyze. And as you can see now from the pictures, we now need to run model to measurement comparisons, which they need to be backed by as many real ground reference sites as possible. Okay, the more sites we compare with, the better. We then need to have metrics of different kinds that allow us to identify the factors that are affecting the model performance. This includes measuring bias, which represents more the systematic deviations, as well as detecting random or non-systematic deviations through other metrics, because those are affecting the results of our analysis as well. So looking at these both type of metrics, let's call it systematic and non-systematic, we now have a more complete picture of the model performance. And this is going to help us identify the factors that will have an effect on the uncertainty estimation for this specific model. Okay. Only after these steps are done, we are ready to estimate a site-specific uncertainty for both GHI and GNI. We also want to avoid other, in our opinion, bad practices, we can call, that we still see around in the process of choosing an irradiance model for your calculations. For example, switching the irradiance models only because it shows a higher P50 while ignoring its uncertainty. That really will destroy stakeholders' trust in your financial model. We also see attempts to reconcile discrepancies between models by using weighted averages or different irradiance datasets. Here, just remember that as a general rule, good data plus bad data always make bad data as a result. Then we sometimes see teams using ground references with unknown or low or very low quality. That will remove the value of any comparison you want to do here, okay? And finally, we also see comparisons of statistics for different models that are bringing a lot of confusion to the industry. Here, we don't want model comparisons based on different sets of reference points or different evaluation procedures, because that will show biased and misleading results. So here, the recommendation is to always use independent third-party studies whenever they are available. Okay? So now let's move to the second factor, which is the PV simulation itself. The step where we can say we turn the sunlight into electricity. This is typically shown in energy flow diagrams as the one shown on the slide, where we see how the system ends up generating only a fraction of the energy received from the sun after modeling a series of losses across the simulation. Good, so to get this right, we need absolute precision across models that are built inside the simulation software. So this includes also the own parametrizations and inputs for the models, okay? This is very also important to take into account. But what does it mean? Well, models can differ in their inputs and parametrization, and this aspect should always be considered, because two models are not necessarily the same just because they have the same name. Understanding how they are built and configured from inside is essential before we compare any results. Good, so this requires a step-by-step approach that needs to look at all the calculations involved. Good, all the calculations involved is too much, right? Or so since this can be a really demanding task, a practical approach here is to focus your attention on the most impactful system losses first, like shading, soiling, thermal effects, or inverters losses, for instance, depending on the project. Well, and what are the big red flags here? we must be careful with the data processing chain. Here, I'm talking about approaches that use, for instance, average data sets or end up losing thousands of data points that would otherwise make the results much more accurate. So this is also important. And we also need to be careful and avoid relying on generic default input losses or unverified manufacturer datasheets. This will also penalize the project with extra risk that we could have avoided. This is important. So if we can avoid risk, then go for it. And of course, we must definitely avoid simulators with undocumented algorithms. This will introduce extra uncertainty as well. Good, so let's move to the next slide, which is the third and last pillar we're going to see today, which is the interannual weather variability. This refers to the natural cyclical changes in weather from one year to the next. And to model this, we need to run a full multi-year simulation spanning decades of continuous history to calculate the true standard deviation of the yearly energy series, okay? So here it's important to avoid simplifications. We want to calculate the standard deviation of the annual PV yield series. And note that this value will not be equal to applying the same calculation to the annual GHI or GTI series. Good. Another critical error to avoid here is using mismatched or outdated time periods for your irradiance and meteorological inputs on the other hand. So long-term historical records covering the same periods are needed here to capture the true weather cycles. Good. And here another quick note about an extra factor. It's the uncertainty due to climate change. Well, we only recommend including it if we can reach a similar, more or less, level of precision as with the other factors. Here again, we could say that good plus bad estimates can result in bad estimates, okay? And I am not saying here that this factor is not important. I just want to highlight that doing it well requires effort. And applying a constant factor to cover this does not add any value in terms of accuracy, okay? Good, and now, Dorota, can I ask you to reveal the results of the poll finally?
Yes, so you should see the results on your screens.
Good. So yes, so a couple of minutes ago, we wanted to know that based on your experience, which of these three factors was the biggest source of uncertainty if you're in your project assessment, right? Good. So I see that, well, there is a lack of consensus, I see. And this actually points to the right answer, which is it really depends on each project. Okay. And on the next slide, I am trying to summarize these key factors that are pushing the uncertainty up and down, and that may explain also the results of the poll, okay? So first, the solar irradiance model, their uncertainty increases when there's a lack of transparency or there's a lack of standards, which is the case, a very usual case, while improvements in satellite technology or their translation into higher resolution models really help reduce the uncertainty. On the PV simulation part, generic software setups or very simplified assumptions can push the uncertainty up. Whereas more sophisticated models and inputs help bring it down here, okay? And finally, with the interannual weather variability, relying too much on average data can increase uncertainty. While, on the other hand, using longer historical data sets will provide a more reliable picture and reduces the uncertainty here. But in the end, we can say that each uncertainty factor also depends heavily on your project site. It also depends on the power plant design complexity, of course, and this is also very true, the engineering team's active approach to removing the uncertainty along the process, right? We also need to be active here if we want to remove something. Good, so now the next slide, please. We are going to quickly look at a specific real-world case study to see what this means for your bottom line, okay? Good, so we modeled a 10 megawatt project located in Almeria, in Spain. First, you can see the numbers there. We have built the, let's call it the low-cost pathway, okay? And here, by using perhaps cheaper, less consistent data or default software assumptions, our total aggregated uncertainty lands at a high 10.7%, plus minus always, with uncertainty plus minus percent. Because of that, high risk, the lender will only provide a 75% debt sizing in this case, forcing the developer here to pull more than 1.8 million of expensive equity out of their own pocket. And here, your P90 return on equity drops down to a 7%. And now look at this other table here. In this case, we have called this the high fidelity pathway. So by upgrading to higher quality software modeling and utilizing the lowest uncertainty data set possible, we slash our total project uncertainty down to just 6.3% in this case. Because we proved the downside risk is lower, okay, now the bank feels safe increasing our leverage to up to 78%. These are more like 3 points more. And that means in the end that your required equity investment instantly now drops from the last 1.8 to the actual 1.5 million. So a lot of saving. So what happened here? So for this specific sample 10 megawatt project, every single 1% drop on the uncertainty brings you more than 60,000 of cash back into your pocket. And furthermore, this higher uncertainty allows your engineering team to cut other expensive over design margins, and it opens the door to cut your capex even further.
Thank you, Pablo, very much for sharing this sample project with us and modeling how much reducing the PV yield uncertainty impacts the project finances. And do you remember at the beginning, we said that engineers, investors, and lenders ask different questions. So what if I told you that all their answers are related to uncertainty? Now, let's take a look at where these roles overlap, because that's where the shared interests merge. Investors and engineers both care about adjusting project costs because lower uncertainty avoids over-design and lowers the project cost. Engineers and lenders share an interest in ensuring debt repayment because a tighter design supports a stronger P90. And finally, lenders and investors both focus on balancing equity and debt because lower uncertainty enables more efficient leverage. And right at the center is where all three overlap. They all want to reduce PV yield uncertainty. The good news? Reducing uncertainty doesn't require massive investment. It just requires the right data, the right models, and the right approach. And for that, we are here. Do you remember the three uncertainty factors Pablo walked you through? So let's map them to how we at Solargis help you reduce each one. So first is the solar irradiance model. This comes down to the quality of our data, and this is really where we stand apart. Solargis has the most extensively validated commercial irradiance dataset on the market, independently ranked #1 by the International Energy Agency for the lowest average deviation metrics. Our data is validated at more than 300 public sites globally and spans more than 30 years of history. And over the past 16 years we've been operating, Solargis data have become the industry standard, trusted by the market, backed by our strong reputation, and accepted by lenders, investors, and other stakeholders. And we cannot forget about site adaptation surveys. And this one deserves a special mention because if you want to push uncertainty to the absolute minimum, this is how you can do it. Site adaptation surveys calibrate Solargis model to local conditions by combining our satellite data with your on-site ground measurements. But we did a whole webinar on site adaptation a few weeks ago where we explained exactly how it closes that gap. And you can find the recording on our website in the resources section. Second, we spoke about the PV simulation. Solargis PV simulation uses ray tracing technology and Perez all-weather sky model. Our ray tracing algorithm is based on Monte Carlo backward path tracing, and the simulation software uses 15-minute time series data spanning more than 30 years of history by default. And our physics-based soiling model is driven by satellite-derived atmospheric inputs such as PM2.5, PM10, dust, precipitation, and local climate conditions. And the model is validated at 51 sites globally. And the third factor is the interannual variability. This is the natural year-to-year fluctuation in weather, so it's not something we reduce, it's something we measure accurately. And accuracy here depends on history. With more than 30 years of history, you properly capture that year-to-year variability instead of guessing from a short window. We derive it from actual PV out, not just GHI, so it reflects real energy output. And we use the full time series rather than a simplified TMY shortcut. So you're not reducing the variability itself, you're making sure it's represented correctly in your total uncertainty. If you have a project in Solargis Evaluate, site-specific uncertainty is already included. You just need to go to project data, find uncertainty, and activate it. Once it's requested, the uncertainty will be calculated by our experts and added to your project. It only takes a couple of hours for the uncertainty to be delivered. But once it's calculated, it appears in the analysis section at the very bottom, and you can see GHI and DNI uncertainty tables for further analysis. Good, and with that, let's open it up for questions. So if you have any questions, you can leave them in the Q&A panel on your right. We still have around 6 minutes to answer them, so go ahead. So I see that we already have some. So the first question is coming from Erin. How many years of data do you need as a minimum to be able to reasonably calculate PXX values?
Well, yes, I can answer this one. The answer here would be like the higher number of years you have, the better, right? The thing is that we have a technological limit here, which is determined by the satellites. Satellite missions, they started at different years to cover the data that are used for models. So for so the Earth is divided in several like satellite regions. So in Europe and Africa, we have data since 1994. And for Americas and Asia, we have it since 1999. And then for the Pacific area and Australia, we have it. We have the satellite missions since 2007, if I'm correct. So this means that we would love to have like a longer periods, but this is what we have. and the advice here, let's use it all. So if we have 30 years, let's use the 30 years we have. If we have less because we are in different region, let's use what we have. So this is always the recommendation, and yes, that I hope it is answered the question.
Good, thank you. Another question coming from Jaya Krishnan. Sorry if I mispronounced your name. And he's asking P70, P50, or P90, which one is generally used by bankers for a loan purpose?
Well, we see, I have named in the presentation the most popular ones. Yes, P90, P75, P99, yes, to consider the like a very conservative scenario. However, I mean, in a way, it doesn't matter. I mean, like, it's always the same curve we have, and we can make whatever PXS just by multiplying by a different factor. Because as we were showing in the presentation, we have this probability curve that we assume it as a normal distribution, and it's just a matter of changing the factors. So probably in one hand is whatever you like, it's okay. It just is very important that you indicate what you are saying. So you cannot say this has plus minus X uncertainty. You always have to put if this uncertainty refers to P90, which is 1.282 standard deviation, if it is referred to P99, which is like a higher factor than that, and so on and so on.
Thank you. Another question coming from Besmir. What sources do you use the most for historical weather data?
So for historical weather data, we use our own model that is based on satellite imagery. So connecting this to the first questions, we have the satellites covering like they are covering the Earth in a geostationary way, which means that they are always looking at the same part of the Earth. So we count on images from these different satellite areas, and we, based on that, on the imagery we have from that, on the data we receive from the satellites, we are able to build the solar irradiance data set. Okay, this is for solar irradiance. There are many more models inside it. There's a lot of information in our website and our knowledge base if you are interested. Just for the solar irradiance part. Then we also need to look for other data that are influencing the simulation, and they are typically requested also for in the simulation software. Those parameters are temperature, wind, albedo, etc. So for those other parameters, we typically use numerical weather prediction models that we also use another layer of adaptation on top of that to make sure that all data is homogeneous and have the quality enough to be used for the simulation.
Thank you. We have time for one last question coming from Alex. Which uncertainty component typically stands out the most in your analysis? I'm particularly interested in the PV simulation group.
Good. Alex, thanks for the question. I'm very interested as well, and I'm saying here that from the three pillars, this is probably the one that deserves more research still. We need to share more information, do more analysis on what models performs better on different conditions to be able to quantify this factor. So if you are interested, we can share some papers, but as I say, for this factor, we have probably less research involved, so we can determine the exact number of this uncertainty, which are probably not so high degree of accuracy.
Thank you very much. We have a lot of questions coming in, but we are on top of the time. And the ones that were not answered will be followed up in an email, okay? So if you're interested in learning more about how Solargis can help you reduce uncertainty in your own projects, you can reach out to us via contact@solargis.com or go to our website to fill out the contact form and we'll get back to you. Thank you for joining and staying with us until the end, and we wish you a nice rest of the day. Goodbye.
Thank you. Bye.